Hello everyone, welcome back to the MP Coding Linux Device Driver Development Series with Raspberry Pi. In the last video, we discussed the Linux I2C basics. There, we talked about the user space I2C driver, the I2C adapter, and the I2C client concepts. Today, let's take the next step and create our own custom I2C client driver on top of the Linux kernel I2C core, using BMP180 sensor. In the previous video, I also showed you some useful I2C tools app commands. Using this command, we can list all I2C adapters registered with the kernel. Here, you can see I2C1. This is the bus where I have connected the BMP180 sensor. The other two adapters you see are related to internal HDMI connections. If you do not see I2C1 here, that means you have not enabled the I2C interface in your Raspberry Pi configuration. If you are not sure how to enable it, please watch my previous video or follow the steps mentioned in the README file. In this example, I am going to use the BMP180 sensor. But if you do not have a BMP180, don't worry. For the first part of this video, you actually do not need the BMP180 sensor. You can use any I2C compatible chip or even an Arduino, ESP32, or any other board configured as an I2C slave. In future videos, when we discuss device tree concepts, I will also show examples using the ESP32. Now, if we look at the BMP180 sensor datasheet, we can see the application circuit. The BMP180 consists of a sensor, an analog-to-digital converter, and a control unit with EEPROM and a serial I2C interface. The BMP180 provides uncompensated temperature and pressure values, which we later process using calibration data. You can refer to the datasheet to understand the internal details of the sensor. I am using this BMP180 sensor mounted on a small breakout board, which already includes a voltage regulator and I2C bus pull-up resistors. Because of that, we can directly connect the sensor to the Raspberry Pi without any additional components. Now, if I scan the devices on the I2C bus using this command, you can see the hexadecimal value 77 appearing on the bus. This 77 is the I2C address of the BMP180 sensor. Okay, now let's create our first I2C device driver. Here, I have created a new makefile and a source file. In the source file, for now, it only contains empty init and exit functions. At the top of the file, we need to include the linux/i2c.h header. This header provides the kernel APIs required to write I2C client drivers. Next, we need to define an I2C driver structure. So here, I am creating a static struct I2C driver, and I will name it my driver. This I2C driver structure contains standard driver model callbacks, such as the probe and remove functions, and other driver-related callback functions also. Here's struct for device driver, and an I2C device ID table, which is used for device matching. So first, let's add the probe and remove functions. I will create two static functions called my_probe and my_remove. In the probe function, for now just set the return value to 0. Pass these function pointers to the I2C driver structure. .probe equals to my_probe. .remove equals to my_remove. Next, we need to define the I2C device ID table. If we look at the definition of struct I2C_device_ID, we can see that it contains a name field and a driver_data field. This driver_data field is private to the driver. It is of type kernel ulong type, which is essentially an unsigned long. This means we can store any private data that fits inside an unsigned long, and later retrieve it inside the probe function. So in the source file, let's define I2C device ID table. It is type of struct I2C underscore device underscore ID. I will define it as a static array and name it my underscore IDs. At the top, I will define a private data structure for the driver, and I will call it struct my underscore data. Inside this structure, I will add a character array to store a name string and an integer value to store some number. These fields are just for demonstration to show how private per device data can be passed to the driver. You can pass any data structure you want, but the maximum size of the data passed should fit within the range of an unsigned long data type. Next, I will create two sample device profiles. Static struct my underscore data, I will name it as A. Name is set to device A, and the integer value is set to some random number. Second one is device B. Name is set to device B, and again, a random number is assigned. Now, inside the my underscore IDs table, I will add an entry with the name BMP180A and pass the address of device A as private data. Since driver underscore data is of type kernel underscore long underscore T, we need to cast the pointer to it. I will add another entry with the name BMP180B and pass the private data for device B in the same way. The last empty entry is mandatory, and it marks the end of the ID table. Now, we attach this ID table to the I2C underscore driver structure. And we need to do one more thing, export this ID table to user space. For that, we use the module underscore device underscore table macro. Here we need to pass the bus type, which is I2C, and the device ID table, which is my underscore IDs. The driver underscore data field is commonly used to support multiple device variants using a single driver. In real drivers, this private data is often used to store feature flags or device capabilities. Inside the probe function, the first thing I want to do is get the device ID information associated with this I2C client. For that, we have this helper function call I2C underscore client underscore get underscore device underscore ID. We just need to pass the I2C underscore client pointer, and this function returns a pointer to a construct I2C underscore device underscore ID. Pass the client pointer here. Let's get the return device ID struct pointer, and I will name it as ID. Now, using this ID pointer, I can print the device name that matched from the ID table. Next, I want to access the private driver data that we associated with this device ID. As we discussed earlier, the driver underscore data field is of type unsigned long. So here, I will cast it back to our custom data structure, struct my underscore data pointer. Here, I will save that in local pointer name as data. Now, I can access the fields inside this private data structure. Here, in this line, I will print the name string and the integer value stored inside my underscore data. So this confirms that the correct device ID was matched and the correct private data was passed to the driver. Now, I will do one more thing inside the probe function, which is specific to the BMP180 sensor. If we look at the BMP180 datasheet, there is a chip ID register that we can read to verify communication with the device. For the BMP180, the chip ID register is located at address D0, and it should return a constant hex value of 55. Here I will print the address D0 value returned from the sensor. To read a byte from an I2C register, we can use this helper function, I2C bus read byte data. Here we need to pass the I2C underscore client pointer and the register address hex value D0. If the communication is working correctly, we should see 55 printed in the kernel log. Finally, the probe function returns 0 to indicate successful initialization. This probe function is automatically called when we manually create the device from user space. To create device from user space, we call new underscore device like this. I will show you how it works when we create the device from the driver. Inside the remove function, I am not doing any cleanup. I will simply print a message to the kernel log to indicate that the device is being removed. This remove function is called when we delete the device from user space. Now, let's move on to the I2C driver structure. Inside the I2C driver, we also need to provide a driver name. For that, the I2C driver structure contains an embedded struct device driver called driver. If you look at the definition of struct device driver, you will see that it contains many fields. In this example, I will only set the name field. The other fields are required when we write a fully featured production driver, and you can always look them up later in the kernel documentation. So for this driver, I will give the name BMP180 I2C driver. This name is mainly used by the driver model and will also appear in the sysfs entries. This driver name is independent of the device name in the ID table. It identifies the driver itself. Now, let's look at the module init function. Inside the init function, we need to register our I2C driver with the kernel. For that, we use the function I2C_add_ driver. Here we need to pass a pointer to our I2C_ driver structure, which is my_driver. This function returns 0 on success. If it returns a non-zero value, it means an error has occurred. So here, I will store the return value in an integer variable called ret. If an error occurs, I will print an error message to the kernel log and return the error value. If the driver is registered successfully, I will print a success message. Now, let's look at the exit function. Inside the exit function, we need to unregister the I2C driver. For that, we use the function I2C_del_ driver. Again, we pass the pointer to the my_driver structure. After deleting the driver, I will print a simple message to indicate that the module is being unloaded. That's all for the code. Now, I want to show you one more important thing. Inside the I2C.h API, there is a helper macro called module_I2C_ driver. If we pass my_driver to this macro, it will automatically generate the module init and exit functions for us. If you look at its definition, you will see that it simply calls I2C_add_ driver and I2C_del_ driver internally. So there is nothing magical happening here. It just reduces boilerplate code. However, in this example, I prefer to write the init and exit functions manually, so that I can print custom messages to the kernel log and clearly show what is happening. Okay, now let's build the module. The build was successful. Before inserting the module, let me quickly show you the I2C sysfs directories. Here you can see the currently registered I2C drivers and I2C devices. In this terminal, I will open the D message buffer. Now, let's insert the module. Here you can see driver created successfully. Now, let's again check the I2C drivers and devices directories. Inside the drivers directory, you can see a new entry called BMP180 I2C driver. This is the driver name that we provided in the I2C_ driver structure. Now, if we look inside the devices directory, we cannot see any new device. Okay, let's manually create the device. If you have been following this series, you already know what we need to do next. First, switch to superuser mode, sudo su. Now, let's manually create an I2C device using sysfs. Using this command. Here in the D message output we can see driver name printed as BMP180A, and the device, a private data, also printed as expected. Also BMP180 chip ID register at D0 is read and the hex value 55 is returned, confirming correct I2C communication. So when this new _device command is executed, the kernel tries to create a new I2C device. The name BMP180A is matched against the driver's I2C device ID table. A match is found, and the driver's probe function is called. Now, let's verify the device creation. Check the I2C devices directory again. Here, we can see a new entry. This indicates that a new I2C device has been added on bus 1 at address 77. Now, if we run I2 detect again on bus 1, you will notice UU instead of 77. This means that the I2C address 77 is now in use by a kernel driver, and user space tools can no longer access it directly. Now, let's remove the device. Use this command delete_device. Here in the D message output, we can see that driver's remove function is called. The device is detached, and the I2C address becomes visible again in I2C detect. If we check devices directory, we can see device been removed from the list. Next, let's create the BMP180B device. In the kernel log, you can see that the device BMP180B is created, and its associated private data also printed. Now, let's remove this device as well. Now, let's try creating a device that is not listed in the device ID table. Here, you will notice that the rDriver probe function is not called, so driver does not bind to this device. This clearly demonstrates that only device names listed in the I2C device ID table are matched. Okay, let's remove this device as well. Let's remove the module. Okay, module removed. Let's look again the I2C drivers directory. BMP180 I2C driver removed from the I2C drivers list. Okay, so far, we have been creating and removing the I2C device manually using sysfs commands. This manual new_device approach is very useful for learning and debugging because it helps us clearly see how the driver binding process works. However, this method is not suitable for production systems. In real-world systems, we do not manually create I2C devices from user space. Instead, the kernel itself is responsible for creating and managing I2C devices. So in the next part, we are going to create and remove the I2C device automatically from inside the kernel module using the Linux I2C core APIs. Okay, let's start. I have already modified the code, so now let me explain the changes. Here first, I have defined the BMP180 I2C address. Next, I have declared two structure pointers, one for the I2C adapter and one for the I2C client. The I2C_adapter represents the I2C bus controller, and the I2C_client represents the I2C device connected to that bus. Now, to describe the I2C device that exists on the board, we use a structure called struct I2C_board_info. This structure is used to describe I2C devices present on a board, and this information is used by the kernel to build the driver model tree. To simplify initialization of this structure, the kernel provides a helper macro, I2C_board_info. This macro initializes the essential fields of struct I2C board info, such as the device name and the I2C address. So here I provide the device name, BMP180A, and the I2C address, which is 77. I2C_driver struct, probe function, and the remove functions and ID table unchanged. Now, let's look at the init function. This I2C driver part is unchanged. The first thing we need to do is get the I2C adapter for bus number 1, which corresponds to I2C1 on the Raspberry Pi. For that, we use the function I2C_get_adapter. We pass the bus number 1, and it returns a pointer to struct I2C_adapter. If this function fails, we print an error message, remove the I2C driver, and return the error code. If the adapter is successfully obtained, the next step is to create a new I2C client device. For that, we use the function I2C_new_client_device. Here, we pass the I2C_adapter pointer and the I2C_board_info structure. This function returns a pointer to struct I2C_client. If device creation fails, we print an error message, remove the driver, and return the error code. Once the I2C client is created, we release the adapter reference using I2C_put_adapter function and pass the my_adapter pointer. Finally, we print a message indicating that the I2C device was created automatically. Now, let's look at the exit function. Inside the exit function, we simply check whether the my_client pointer is not null. If it is, we unregister the I2C device using I2C_unregister_device and pass the my_client pointer. So this will remove the I2C device, call the driver's remove function, and cleanly detach the device from the driver. Okay, that's it for the code. Now let's build the module. Okay, the build was successful. Now, let's open the kernel log buffer in another terminal so we can monitor what's happening. Next, let's load the module. As soon as the module is loaded, you can see that the probe function is called, the device name BMP180A is printed, and the private data associated with this device is also printed. And the value 55 is returned, confirming correct I2C communication. Now, if we look inside the I2C devices directory, you can see the new I2C device, just like before. But this time, we did not use the new_device sysfs command. The device was created entirely by the kernel module. Now, let's unload the module. When we unload the module, the driver's remove function is called, the I2C device is unregistered, and the driver is cleanly removed. If we now check the I2C devices and I2C drivers directories, you can see that both the device and the driver are gone. This is how we can automate I2C device registration and removal inside the kernel, which is the correct and preferred approach for real-world systems. Okay, now let's move to the last part of this video and start reading real data from the BMP180 sensor. Before doing this inside the device driver, let me first show you some useful I2C tools commands that can read data directly from the sensor. From the BMP180 datasheet, we know that register address D0 contains a fixed chip ID value of 55. We can read this register using the I2C transfer command. I2C transfer using bus 1 and write to address 77 value of D0 and read 1 byte from the address 77. Let's run this command. We can see the hex value 55 returned. This confirms that communication with the sensor is working correctly. Next, if we look at the datasheet, we can see that the BMP180 contains 11 calibration coefficients stored in its internal EEPROM. These calibration parameters are required to calculate the actual temperature and pressure values, and they must be read once and stored by the driver. The calibration data starts at register address AA and occupies 22 bytes in total. We can read all calibration coefficients using this command. This command tells the controller to write the start register address AA and then read 22 bytes from the device. Okay, let's run the command. You can see the calibration coefficients value are returned. Now, let me show you one more important operation. According to the datasheet, to read the temperature data, we must first write to the control register at address F4 with the value 2E, which starts a temperature measurement. The maximum conversion time for temperature is 4.5 milliseconds. After waiting for the conversion to complete, we can read the raw temperature value from register F6. We can perform this entire sequence from the command line like this. This command returns 2 bytes of raw temperature data. Using the calibration coefficients we read earlier, this raw value can be converted into the actual temperature. The BMP180 datasheet clearly explains the calculation steps required to do this conversion. So in the next step, I will show you how to perform all of these operations inside a Linux device driver, instead of using user space tools. Okay, I have already written the code for this part. As you can see, there is a bit more code here compared to the previous examples. But don't worry, this code is not doing anything new or complex. It is simply implementing the exact calculations described in the BMP180 datasheet. You can find the complete source code in my GitHub repository, so you don't need to type everything manually. Okay, here at the top, I have included some other Linux kernel API headers. We need these headers to create a proper I2C device driver. Here, these register definitions are taken directly from the BMP180 datasheet. You can refer to the datasheet to understand what each register does. Next, this BMP_calib structure is used to store the 11 calibration coefficients that we read from the sensor's internal EEPROM. Then we have this BMP_client structure. This structure holds everything the driver needs: the I2C client handle, the calibration data, and the oversampling setting. Now let's look at this BMP_read_block helper function. This function reads multiple bytes starting from a given register. Here, I am using I2C_sm_bus_read_I2C_block_data. We pass the I2C client the starting register address, the number of bytes to read, and the buffer where the data should be stored. This helper function is used in multiple places, so it avoids repeating the same I2C read logic again and again. Next, this BMP_read_calib function. This function reads 22 bytes starting from register AA. These 22 bytes contain the 11 calibration coefficients. Here, we combine 2 bytes at a time and store them using the correct data types, exactly as specified in the datasheet. You can cross-check these data types with the BMP180 datasheet. These dev_dbg calls are only for debug visibility, so we can see the calibration values in the kernel log if needed. Now let's look at BMP_read_raw_temp. This function reads the uncompensated temperature value. This matches exactly what we did earlier using I2C transfer from the terminal. First, we write the value 2E to the control register F4. Then we wait at least 5 milliseconds. And finally, we read 2 bytes from register F6. This gives us the raw temperature value, also called UT. Next, we read the uncompensated pressure. Here, you can see this command where the OSS value is shifted by 6 bits. This is because the oversampling setting is located in bits 6 and 7 of the measurement control register F4. You can clearly see this in the datasheet. Again, we write to the control register F4 with the command and start the pressure conversion. For pressure, the conversion time depends on the oversampling setting. So based on the OSS value, we use different delay times in milliseconds. You can find these time settings also in the datasheet. After the conversion is complete, we read back the raw pressure data from the sensor. This line here, where the raw pressure value is calculated. This calculation comes directly from the datasheet. You can see the exact same formula defined here. Now let's move to the BMP_compensate function. This function calculates the true temperature and pressure values. There is nothing magical happening here. I have simply implemented the exact compensation algorithm provided in the BMP180 datasheet. You can compare this line by line with the datasheet formulas. Up to this point, everything we have done is based directly on the datasheet. If you don't understand any part of this, please ask in the comment section. Now here comes the important part. Here, I create 2 functions that expose sensor data through the sysfs file system. First, this temp_input_show function. This naming pattern with _show is required by the sysfs framework, and the function signature must follow this format. I'll explain why in a moment. Inside this function, we read the raw temperature data, read the raw pressure data, then calculate the compensated values, and finally return the temperature in tenths of degrees Celsius. Next, this pressure_input_show function works the same way. It reads the raw sensor data, calculates the true pressure, and returns the pressure value in pascals. Now look at this device_attr_ro macro. This macro does the magic mapping for sysfs. Notice that I passed the name temp_input here, not temp_input_show. If you check the macro definition, you can see that it automatically associates temp_input with the temp_input_show function. That is why we must follow this naming convention. Next, in this attribute pointer array, I am passing dev_attr_temp_input.attr and dev_attr_pressure_input.attr. You might notice that we never explicitly define these variables. But if you look at this macro definition, you will see that these structures are generated automatically for us. Then we create an attribute group and pass this attribute array to it. Now let's look at the probe function. As before, we get the I2C device ID and then print the matched device name to the kernel log. Next, devm_kz allocates memory for our per-device data structure. This memory is managed by the device, so it will be freed automatically when the device is removed. We store the I2C client pointer, set the default oversampling to the maximum resolution, and then attach this structure to the client using I2C_set_client data. After that, we read the calibration coefficients and store them inside the client data structure. Finally, we create the sysfs attributes for this device using sysfs_create_group. In the remove function, we simply remove the sysfs attributes that were created in the probe function. The remaining parts are the same as the previous example. We register the I2C driver and automatically create the BMP180 I2C device from inside the kernel. The init and exit functions do not change anything conceptually. They just register and unregister the driver and create or remove the I2C device automatically. Okay, that's it for the code. Now let's build the module. The build was successful, so let's load the module. Here you can see the kernel output. The BMP180 I2C device has been registered successfully. Now let's look at the I2C device directory. Here, we can see a new device created by our driver. If we go inside this device directory, we can see two sysfs entries, temp_input and pressure_input. Now let's read the temperature value. If I read temp_input, you can see the value 200. This means the current temperature is 20.0 degrees Celsius, because the value is reported in tenths of a degree. Next, if we read the pressure_input file, we can also see the pressure value in pascals. So we are successfully reading real data from the BMP180 sensor through our kernel I2C driver. This is exactly the result we expected. I have created a simple test application to read data from this sensor. I'm not going to explain this test code here. You can check the full source code in my GitHub repository. This application simply reads the temperature and pressure values from the BMP180 sensor. Okay, let's run it. Here, we need to pass the device path as an input. Here you can see the temperature and pressure values printed on the screen. And this is how we can develop a custom I2C device driver and verify it using a simple user space test application. The automatic I2C device creation shown here is used only for demonstration purposes. In real embedded Linux systems, I2C devices are typically instantiated using device tree or ACPI, mainly on x86-based systems. We will cover both of these topics in detail in the upcoming videos of this series. In this video, we built a complete I2C device driver for the BMP180 sensor and learned how to read real sensor data from the kernel. In the next video, we'll explore the Linux SPI subsystem with practical example drivers. Please like, subscribe, hit the bell icon. See you in the next video.